In 1912, just after graduating with his doctorate degree in physics, Niels Bohr took a job in Ernest Rutherford's laboratory in England. A year earlier, Rutherford had introduced an amazing new theory about atoms. It was thought that atoms were solid spheres of positive charge with negative electrons mixed throughout. But according to Rutherford's model, atoms look more like tiny planetary systems, with most of the mass focused in the positively charged nucleus of the atom, and the negatively charged electrons rotating around the nucleus, like the Earth around the Sun. Rutherford's new model was a scientific breakthrough, but almost immediately he found a hole in his theory.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms can't exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
Rutherford was ready to give up on his atomic model, but Niels Bohr saw a way to save the theory.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. We'd have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
Bohr's idea that electrons can only have fixed orbits drew inspiration from other new theories that light and energy are waves made up of discrete energy packets, or quanta, now called photons. But most physicists disapproved of Bohr's theory that would apply this quantum idea to matter. In 1926, a 25-year-old German physicist named Werner Heisenberg came up with a matrix-based mathematical description of atoms that supported Bohr's view. But classical physicists remained unconvinced because the math was unfamiliar, the ideas too abstract. In May of 1926, an Austrian physicist named Erwin Schrödinger published his theory on wave mechanics, which offered an alternative to Bohr's particle theory.
The essence of the debate was the electron a particle or was the electron a wave? The Schrödinger school believed that the electron was a smeared out wave. It didn't exist at one point in space or time at all. The electron was a wave that permeated all space and time. Physicists loved this idea. We had a physical picture. We could look inside the atom. Physicists knew how to calculate with waves. They calculated waves as an undergraduate in college. They knew how waves went around and formed orbits. So the appeal of the Schrödinger picture was that it was pictorial. It was almost Newtonian. It was continuous. None of this quantum business. And you could calculate with it.
So who had it right? Was matter made up of waves, like in the Schrödinger model? Or was the Bohr-Heisenberg model right, and matter was made up of particles? The competition to find the answer was fierce.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering How can it be? How can it be that you don't quite know where the electron is? And then in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg's uncertainty principle showed that it is fundamentally impossible to measure the position and the momentum of a particle at the same time with accuracy. The more you know about a particle's position, the less you can know about its momentum. And the reverse is also true. The more you know about the momentum of a particle, the less you can know about its position.
And when he finally had that idea, he realized that he could merge the Schrödinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrödinger wave. So we now have this beautiful synthesis of waves and particles.